If I can quickly interrupt,
Yeah.
I'm going to be passing out just release forms since we're recording this. So if you could just, I'm going to pass them down the aisles, and if you could just sign them and come back. Thanks.
Good morning, everybody. Thank you, Brian, and everyone for inviting me. This is my shortest trip ever to New York City. I came on a train this morning from Philadelphia, and I'm leaving soon.
Thank you.
Hello, everybody.
And you just had a child.
I just had a child, and so if I'm covering any sort of weird stuff, I'm sorry. It's just, this is how it goes. But I'm here. All right, so as Brian said, it's my pleasure to discuss a little bit about the LIGO-Virgo collaboration observation of the recent binary neutron star. And, I'm going to cut to the chase. This is a mostly expert crowd, I think, / hope. So this, of course, is the first, not only the first BNS, which is amazing, but the first multi-messenger event where we had a detection. Susa was exactly right to point out this has been a huge history of this. People have worked on this for decades, and we don't want to, of course, forget any of that. But this is the first time we actually made a detection, and I'm here to tell you about the first 7 minutes. The first messenger in this case was, in fact, Verizon Wireless. So this is kind of a funny event, which I will talk a little bit more about in terms of the data analysis side. And I promised I'd make big promises, and I feel really good about that because for everything that went right in this event, there were as many things that went wrong, and we hope that won't happen the next time. So in reality, when we got this first text message, people logged in, we had a look. We knew a lot immediately. Like, this is literally the first 7 minutes. I'm giving this an asterisk. I'm not a sports person, but I'm told if records have asterisks that mean something important, like you shouldn't trust that. I don't know. So this 7 minutes is too long. So to use an example, the event that just happened 3 days before this, the binary black hole from Virgo, we had that generated and understood in 30 seconds. There's no reason why we needed 7 minutes here, except for a technical one, which I'll get to in a bit. We knew pretty much right away that it was very significant. Only in a single detector, only in H1, the false alarm rate, which is the chance that it would happen randomly by noise, was less than was about 1 in 10,000 years. That's the gravitational wave only signal, not including the fact that we had the GRB. We knew right away that from the point mass estimates made in the online analysis that it was consistent with a neutron star binary. The original point mass estimate was 1.24, 1.53. We knew that there was a compelling association with the gamma ray burst from Fermi. We have an agreement with Fermi. We get some of their events, even low threshold events, I believe. It showed up in our candidate database. And there's automatic software that runs, tries to do the coincidence and calculate, again, the chance that this would happen randomly. And the chance that this GRB and the gravitational wave combined would have happened like this was 1 in a million years. And we also knew this instantaneously. We knew the distance was somewhere between 40 and 50 megaparsecs. It could have been actually bigger than this. The maximum distance was maybe 80 or so. That would have been if everything was absolutely perfectly aligned and it was directly overhead of this detector, which it wasn't. We knew a really coarse sky position. Why did we know only a really coarse sky position? Well, because we only actually detected this in the real-time system in LIGO Hanford. And so when you just have the one interferometer, this is what you get. You think our normal sky maps are bad. Well, here you go. Now you can say, oh, thank you for those 2 detector sky maps. Pretty bad, but we tell you where it isn't. But that's pretty much it. But even with this sky map, we were, and some other fancy stuff, we had distance estimates early on that maybe the most likely value was 46 megaparsecs. So this was useful. And another key thing is that even within this first few minutes, we also, of course, knew the Fermi sky position. Now, the Fermi sky position is not great either. That's what's shown here in this kind of purplish color. It was, I believe, 1,100 square degrees. No one's going to call me out on that. I'm going to go with yes. Thank you.
That's the final one.
Close enough. So 1,100 square degrees for Fermi, and then the integral timing band, which I confess I don't know exactly when this was first made available, but presumably it was available reasonably early on. Was this, and well, I'll talk about it later, but we can get the full gravitational wave sky map initially. Why? Well, there were two two reasons actually. So 2 out of 3 things went wrong, if you want to think of it that way. This happened in Livingston. So this is this time frequency plot. When this was in our paper, right? But when most of you will probably think of the cleaned version of this. This is frequency on the y-axis, time on the x-axis. The 2 x-axes are different. This is minus 10 seconds up to coalescence. You can see the chirp in the LIGO Livingston data, but then you can also see this, right? And here, if you look at the strain, like that's what if you got a neutron star merger that does this, we'd be very interested in knowing
But
that.
you're not able to filter out like you were with the other events, right?
To filter out this. So
Yeah.
here's the thing. Yes, we were. This again. So maybe we can like bad things squared. Eventually we'll get up to like bad things that happen cubed or something. This normally would have been handled decently well by the real-time system. So the real-time system is naive. It will, when it finds something like this, it'll chop it out in a sensible way and move on. The problem here was that this happened within a sort of a second of the coalescence. And we considered that at this point to be no recovery, like an unrecoverable kind of scenario in the code. Turns out that was probably not a good assumption. I mean, in the case when you get an SNR 30 BNS, who would have thought that?
Yeah.
You can still do something. We've already fixed it. We can do even better, but this exact thing, if it were to happen again, shouldn't be an issue. But that's not the only thing that went wrong. So also, this was around 8:40 a.m. on the East Coast. Somewhere in the middle of the night, the Virgo data transfer had gone down. So we were missing Virgo data also. Now, that's also the reason for the 7 minutes. So when I claim these big promises, like the 7 minutes was literally because the analysis will wait for all the data and then time out. So normally it would be able to analyze things within 15, 20 seconds, but it was waiting for the Virgo data and it kept waiting and waiting and waiting and then would time out and then just keep going. So 6 minutes or 6.5 minutes of the 7 minute latency was just waiting for Virgo, which is okay. This is, of course, what it looks like clean, much nicer. And like I said, there's a lot of work, so this is right. Like we should be able to do a really good job of this online. I mean, computing is becoming something we have a lot of now, fortunately. But even the naive thing would have meant that this was a very different kind of event if we would have just not had this one particular corner case.
So, Chair.
Yes.
So you mean in the future this will be very precisely, intelligently removed in O3? So.
Yeah.
This will be easy. Okay.
Yeah. I mean, it was already, actually, no, I wouldn't go as far as saying intelligently, the thing that we did in O2. So this should have been done correctly in O2. The only hitch here was the closeness to coalescence. Had this been a second earlier, we'd have been fine. It's moderately intelligent what we're doing now. We could do better. Like the stuff that people did actually figure out this data in the end was fantastic. If we can get that automated in real time, that would be wonderful.
That's my question.
Whether or not that'll happen by O3, I can't say. But people do some sophisticated glitch extraction just to fill everyone in. That was better than what we would do naively.
Did you see what the origin of the glitch was?
I think this is a photodiode saturation.
I'm not 100% sure that is the case. It's a possibility.
It was flagged by the photodiode saturation software.
It is a photodiode
But we don't know what
saturation,
caused
but
it.
that's not the code.
Yeah.
Okay.
Yeah. So when
There
something
needs to be a code for the photodiode
Yeah.
saturation. Yes, it
So-
is a photodiode saturation.
Yes. So there's an automatic system that determines when you've hit the dynamic range of some photodiode somewhere, and that'll cause a glitch like this. The actual origin of it, I'm not entirely sure.
So,
We don't know,
So
actually.
you're talking about
We
glitch
don't know.
removal, are the glitches of this origin, or disappearance frequent, or do all the glitches look the same?
Too frequent. Yeah, things like this are too frequent. I mean, that's what it boils down
They all
to.
look pretty much the same?
They look pretty, yeah. Well, I mean, we have a lot of different glitches, but I mean, this is a very narrow feature, which makes it, of course, very broadband. And there are a lot of things that data like this. And the thing is that when when you talk about black holes, which are maybe, the same time scale as this, the probability of getting them on top of one another is small. BNS, if you started integrating at 15 hertz, this thing was 6 minutes in our band. So you're going to get unlucky, unfortunately. And this is a case of that. This is a particularly egregious case of getting unlucky.
You're still very lucky.
Yeah, we're still very lucky. Thanks. That's better perspective.
Had it happened a
Could
minute
happen a week
earlier,
later.
if the glitch had happened a minute earlier, you would have much much better.
Oh, if it would have been a minute earlier, it would have been
Okay.
cake.
No.
Even a few seconds earlier would have been wonderful. Yeah. Okay, so that was the first 7 minutes. Within the next 4 hours to 10 hours, a lot of people were working really hard to clean, the L1 data, to transfer the missing Virgo data, to get this all going. The collaboration produced the first sky map at 4 hours, and another update around 10-ish hours. I should have looked up the exact time. And the bottom line is that then included not only all the LIGO data streams, but also Virgo. Virgo was mostly in a null, so there wasn't much SNR there, but that still helps pin down the sky position. We got it down to about 30 square degrees. SNR 32 was the final answer here. So that's the combined SNR. It's this quadrature sum of the SNRs of the different detectors. Virgo produced essentially nothing. Livingston was actually the highest SNR. So it was unfortunate that that was the one that was missing at the beginning. Like I said before, if you would have started this thing at 15 hertz, which is what the online analysis actually does, it starts integrating very early, with 6 minutes in there. So over the next 2 months, fast forward until Monday, it really was about exactly 2 months. We found out, of course, things we may have already known, but we found out some more stuff too. It's consistent with a 1.4 solar mass binary rounding. We actually quote a little more precision on this. 2.74 solar masses total. This is the posterior PDFs for M1 and M2, so you can see the actual joint PDF, and this really thin sliver here is the function that creates this thin sliver is the chert mass, which is a special combination of the two masses that you measure extremely well. It basically controls the phasing of the in-spiral, so it's the thing that you sort of phase lock onto when you're doing a matching. There are two different posteriors, one with assuming that the components had a very small spin, and that's the blue one, and the other one assuming that they basically spun so fast that, I think the 0.89 must have come from, take the most compact equation of state, spin it until it blows apart or something. I don't know where 0.89 came, but that's huge. I mean, it's bigger than what I would think of for being physically reasonable if it's a neutron star. Actually, I mean, in theory, actually, to be fair, one of these, and I should point out, we're pretty sure that they weren't both black holes for obvious reasons. One of them could have been a black hole. Now, it would be an unusual black hole. We can't say. We can't say. We can put bounds on the compactness, but we weren't able to measure any effects that were definitively not point mass-like. So we can try to measure the neutron star getting, elongated and measure the tidal field induced in the neutron star, and we were able to bound it, but not say for sure. So one of them could have been a black hole, though it wouldn't be the smallest black hole that's known if that were the case, because we're really sure about the masses.
So, sorry, the notation chi is
Chi.
related to the spin.
It's
but
the
what is
spin.
it?
It's the
total spin, or it's
specifically this is the spin relative to the maximum allowed in general relativity for a black hole along the z-axis, which is
defined by the orbital plane.
defined by the orbital plane. Thank you. Good. Anything else? Okay, so the mass ratio is pretty well constrained, especially if you look at the small spin, which, if you believe that this is consistent with other binding neutron star observations, it's not really the case. So pretty small mass ratio, or pretty narrow mass ratio rather. Like I said, we knew it's compact, but I'll talk a little bit more about the tidal stuff in a second. In terms of remnants, we're not sure.
Is the low spin case virtually equivalent to if you assume they were non-spinning?
It's not. It's close, but it changes things enough.
So if you said they were non-spinning, you could get
Even
potentially
tighter. Yes, and that's a great question. And of course, we can play this game with priors until everyone's blue in the face. But there are observed spins in neutron star binaries up to like 0.04 or something.
Right. Yeah.
So,
reasonable, but
yeah. So basically, we wanted to put that in because basically what it'll do is, as you can tell, the first order effect is that it broadens the mass ratio.
it still might be interesting to quote eventually have someone do
Agreed.
the analysis for
Agreed.
zero spin case
Agreed.
just to understand.
Yeah, I agree. Yeah.
So people are interested in the history of the 0.05 choice. Yeah. So in a sense, you choose something which happens to produce something that agrees with observed something before. Yeah. So what is the history of that
So
choice?
the 0.05 comes from, as far as I know, just the known sample of binary neutron stars, not necessarily isolated neutron stars.
Okay, so there is some physics behind.
Yeah.
I think it's sort of what we know about their spin. I don't know whether it's from what sort of measurement and estimated what their spin would be at the merger. There is an extrapolation from our own known galactic binaries into their spin would be at merger time. And for me that makes completely sense. So I actually like it.
Yeah.
So the most people find that parameter kind of ad hoc in the paper. So maybe
I see. No, that's fair. So
Yeah.
I guess I hadn't appreciated that. Yeah, I assumed maybe more were aware of that.
And-
But it comes from observations, is the point.
there is no more question. So in a sense, on the previous slide, you alluded to the sky position and the SNR between detectors.
Yes.
So there are two factors there. So L1 was twice as sensitive
Yes.
as H, and H was twice as sensitive as Virgo.
Yes.
So that's one factor. The second factor is the sky position. So are we lucky with the sky position, and that's why Livingston is better, or Livingston is a more sensitive detector? So I think explaining the interplay betwn lock and detector sensitivity is interesting.
Yeah, I mean the detector sensitivity is, like you said, about a ratio of 2 at this point. And I mean, the sky position was a little bit unlucky for Virgo, I think it's fair to say. But I think the dominant effect between Livingston and Hanford was in fact just the detector sensitivity difference.
I think the antenna factors were very similar.
They were very similar, yeah.
Yeah, I mean, they are sort of the way
Yeah,
the
exactly.
rotation is only 15 degrees with them in
Yeah.
cases. That's,
Absolutely, yeah. And generally speaking, most of the events they're comparable. So
yeah.
the SNR ratio tends to come from the actual sensitivity of the detectors.
You know, can I?
Yeah.
About localization, so
Yeah.
so Virgo, it was in a blind spot of Virgo, and
Yeah.
we were told that this was actually helpful.
Yes.
How much better, or would the localization be actually worse if it was not in the blind spot of
It-
Virgo and
Wow, that's a great question. You know, I'm going to answer it, but I'm only going to be able to give myself like a 95% on this one, whether or not it's right. So you'll have to take the 5% with it. Maybe I'm wrong. I think the answer is that you should always get a better measurement when you actually have definitive signal. So, but that being said, I mean, like the data not having something there does constrain the sky quite well, and that's what you're seeing here.
Chad, can you go back to the sky map?
You had the sky maps up with the
Yeah.
comparison.
So actually the antenna factor for Virgo here was pretty good, okay? So Virgo definitely had us to put it into this one.
Yeah, the faded region is just L and LIGO and
And then the rest is rest within this region. I think it's coming that they do have the little 2.7 SNR. There was a lot of back and forth thing whether the claim of is it in the blind spot, and Virgo people saying no, it's close to the blind spot. So
Yeah, I mean,
they say there is a 2.7 SNR or something in there, which is not visual on the certainly on the spectrogram, but you know.
Yeah, I can give you my take on this from my side of the Virgo contribution. So unlike the black hole, the GW 170814 black hole, where the SNR in Virgo was still low, but there was an actual peak, right? So like there was a peak in the SNR in time, which indicated this is sort of the time when the best fit was, that corresponded to a coherent signal, arriving at Earth. In this case, whatever signal was there in the data was so low that it didn't even cause really a peak at the time of this event. It was sort of below a nearby, just random fluctuation. So it was very low, to give you a sense of that. I mean, the mean in this, and once you've maximized over phase, is like 1 point, what's square root of 2? Okay. Oh, sorry, I went too far. Yes, good. So we don't know for sure what the remnant was. This is actually ongoing work, so the LSC is still working on this. right now we've said we can't really say, and that's not surprising because the neutron stars, if they form a black hole, I mean, we're talking about bring down frequencies that are like 5 or 6 kilohertz. So this is really at a part of the detector sensitivity which is not very good. I actually
Practice
have.
being lucky.
I have two laptops with me. I'm not kidding. This is the level of redundancy that you can expect from me. There's another one in my bag.
Yeah, that's apparent.
That's right. Okay, so the rate. So I added this, sort of remind folks of what this was. So our best estimate of the rate at this point, and we're going to do a more careful job of these things at the end of the run. Not that it's going to change much, but we did something reasonably quick and dirty on this to get 1,500 mergers per gigaparsec cubed per year.
So what are the assumptions that go into that?
Yeah,
Because that's 1.5% of the supernova, right? So
Yeah,
that's
yeah.
outrageous.
Yeah. So that's good. So we have. I believe this is taken uniform over 1 to 2 solar masses. So that's one
Uniform
thing.
mass distribution.
Uniform mass distribution.
Okay,
So that's
so,
one thing.
yeah.
Which probably will change it a bit if we put in 1.4. We put a threshold, it's basically a threshold calculation, and that's not going to change much. We assumed that we would detect these things at a 1 per 100 year false alarm rate. Expect a more thorough rates calculation soonish, meaning that we'll be able to provide different mass priors and different slices of the data.
Right.
With
the
a-
lower band is about 500, and the upper band is like 5,000, right? There's some-
Yeah, it's pretty asymmetric. I should have put the 90% down.
Up, maybe.
Actually, it probably won't change a ton, actually, because it turns out that the average of the 1 to 2 is actually pretty close.
Okay.
So it may change a bit, but there'll be definitely more slicing of this than, and like I said, a slightly more careful job. What we did now was pretty careful, but we also wanted to get everything out in 2 months.
Right.
And so for example, we are going to recalibrate all the data, do some cleaning of HD. I mean, there's like a bunch of after the fact post-processing that we've, sort of piled up, not done yet.
Right. And you can split the priors.
Yeah, we can, exactly. So there'll be a thorough account of this. Probably it'll take a few months, but people are working on it. All right, so really briefly, I know I'm probably already out of time. We were able to constrain the tidal deformations of the neutron stars, lambda 1 and lambda 2. That's how much they get deformed by the non-uniform gravitational field on the binary. And the bottom line here is this is the PDF. We solved for the tidal deformations of the 2 sources separately, again for different spin priors. The color is the ability to constrain 90% contour, 90% contour. To make a long story short, we constrained some equations of state. The equations of state make these curves, and if they're above this, then they're constrained. These are things that maybe not super favored to begin with from other observations. So I'm not saying that we did anything here that was extremely profound, but the fact that we were able to start doing this so early, I think, was surprising to us even, because we thought maybe this was a lot of years out, and so it's promising that we'll have a field that is actually observational neutron star physics sooner rather than later.
Stiffer is upper right there. Stiffer equation.
Stiffer is to the right.
Stiffer means less compact because it can support itself. Sorry, I wanted to get to the juicy stuff here at the end. I know we're running late. Really briefly, another surprising thing. So people made a run, so the LIGO Scientific Collaboration made a run to calculate the Hubble constant from this data. And we were able to do that precisely because of the multi-messenger aspect in this case. So in the local universe, the Hubble flow is related to the distance to the Hubble constant. The trick here is figuring out exactly what velocity is associated with the actual expansion of the universe. So there was a study to look at this NGC 4993 galaxy where it was located, and to try to get an estimate of the actual Hubble flow there. And anyway, with that, we know D, the luminosity distance, extremely well from the gravitational wave side. They're basically standard science. Given the parameters, you can solve for D. If you know all the other parameters, you can solve for D. It's true that we don't know D perfectly, but we know D to some extent. So we're able to solve for H naught, and this is the blue curve is what we get. Compared is Planck and one of the supernova surveys, the most recent one. So yeah, it's pretty broad, but still kind of cool. Afterward. That was just to set up this. So of course, instead of trying to figure out the Hubble constant, we can assume that one of them is right. And this, along with the sky position and everything that we get from the electromagnetic counterpart, right? Because we wouldn't have had such precision on this from the gravitational wave alone, means that we can actually go back and ultimately constrain parameters better than we would have been able to with the gravitational wave alone signal. So one of the things that's of interest probably to this group is the viewing angle, which is like mod pi of the inclination. Did I get that right? Yeah, okay.
This one was twisting away from us, but then.
Yeah.
But this is angled.
Yeah. So we don't determine between. So this doesn't determine between counterclockwise or clockwise rotation. But so the viewing angle of this, if you use Planck, it's 28 degrees for the Planck value of the cosmological constant, 36 degrees for the shoes. I'm actually blown away that it makes such a big impact on us. I would have never guessed. It's kind of cool. So you can see, how these measurements all feed together, and it's kind of wild. So maybe a number you want to keep in your mind is take a Planck weighted average of that. Sorry, that was just a little joke. Maybe 30 degrees. Keep it in the back of your head. Okay, so was this picture right? Well, Brian, was it right? You'll tell us later. Some parts, exactly. So there are some cool things. Yeah, a lot of parts were really pretty amazing. The GRB observed was 10 times closer. I'm sure you hear about that. It was significantly weaker than other GRBs. So what's going on with that? We can go back and look at the viewing angle, the beautiful viewing angle in this original plot. I put in less than or equal to 30 degrees.
That's about right.
It's about, yeah. And so this is what we saw. Now the thing that we may not have expected, or that's a little surprising, is we got gamma rays, although admittedly in kind of a strange way. So we're probably seeing it off axis, but we have things that we normally associate with on axis. So there are some mysteries there, and I'm not going to speculate too much on that. That's what the rest of the group here for. But the question is, if this is common, are we missing some stuff? Are there other prompt emission mechanisms that we could maybe hope to find, or what do we do? What do we do? All right, so I want to pose another what if, and I promise I'm getting to the end. This was actually a beautiful signal where some stuff went wrong that was technical, but in the end we were able to get a 3-detector signal out within 4 hours that had a pretty good sky localization, clearly good enough. But we could have been even more unlucky. The fact of the matter is, a lot of the time we don't have 3 detectors running. We don't have 3 gravitational wave detectors running. We have a lot of time where there are just 2. We have a lot of time where there's just 1. So we still want to be able to look for these things. And the question is, what would we have done if we would have only had that single H observation and we really didn't have LIGO or Virgo? So we could have sent out, we did send out a GCN, and we would again, and you would have been left with this purple. But then, if we would have had integral, you would have actually maybe been able to do that. So I don't know at what point it gets small enough that people will actively follow up the short GRBs if LIGO can tell you nothing except we're pretty sure a neutron star emerged. But it's something to think about, because it's otherwise going to be one of the bigger selection effects until we have 5 or 6 gravitational wave detectors. Right? If these things are not that common, we want to get every shot at it we can. So this is something to think about. Can you do anything to make it convincing to follow up these events, even if we can't tell you as much with gravitational waves?
What was the triple coincidence time for the 3 detectors in August? How lucky was it that they were all 3?
I actually don't even know what it ended up being with Virgo, but it wouldn't have been extremely representative, probably. Does anyone remember off the top of your head what the triple was? Historically, double has been no more than 50% of calendar time, and so triple's even
but
worse.
we were really making an effort. This is the reason why Hanford was running the way it was running, so it would be running safely. I don't have the number. It could be around 50% in August for triple.
It could have been. It could have been that high. It was pretty good, actually.
So Jay,
really, I'm sure it's going to come out in a different way.
LIGO promised factor of 2 bigger network sensitivity on the press conference. Yeah. So
promise, you said.
Yes.
Yes. Oh,
That's what they
I
do.
forgot about that detail. That's great. Good.
Yes, so
They
that's
promised it that.
so people are having very optimistic views that, oh, we will see these things once a week, and I don't believe any of it. Yeah. So even with factor of 2 higher sensitivity,
You mean in 03, sorry?
in 03, yeah.
No,
So
I don't
so what is the value of this thing? Right now the value of this thing is hundreds of millions of dollars because we have only one. So what do you expect from 03? How many more of neutron stars we will see with decent signal to noise ratio which allows additional science?
Yeah, this is an important point. So I mean, SNR 30 for this one, right? We really probably should have had a couple at SNR 12, right? I mean, it's small number statistics, so you get what you get. But I think you fold that into how the rate works out, right? And so, so if we really did get a factor of 10 bigger volume in 03, I would be a little bit shocked if we didn't detect of order 10 neutron stars. So maybe that's not one a week, but one a month seems possible. Now, will they all have short GRVs off axis? I don't know. We gotta look.
I have a question about this, and maybe you already said it. So if in the worst case scenario you have one detector and you've got these two things and you have that sky localization, with one detector, how good's your distance error?
So if we actually fold in additional sky information, it can get pretty decent. Like, we can give you a maximum distance because we know we can measure the gravitational wave amplitude decently well.
Right.
And so basically we can then assume it's right overhead and lying right at us. So we give you a max distance, no problem. With a little bit of extra sky information, we can do even better than that. And though the max distance and the mean distance only differ by about a factor of 2, so you can narrow into I mean, you might still be talking about 30, 40, 50% errors. But if that's acceptable, then we can give that to you. Even with one detector.
Okay.
Yeah.
Finish up watch.
Yeah. Okay, sorry. So, missing piece is this. We observed a lot of electromagnetic counterparts. This is something we'll hear about next. But we didn't observe any of these wavelengths before 10 hours. So, if there's a story to be learned from this, we need to do better. And so, in my opinion, the conclusion on this, I would say, is the next frontier is try to get the promptest emission in broader wavelengths to find out what's going on at this, initial collision. And some questions I might have, are we missing some local population of transients associated with relatively nearby neutron stars? Probably, I guess. And then this one I've already asked. Can we do better if we have the selection effect of fewer detectors? And that's all. Thank you.
Time for a couple questions. Right?
So this is pretty much an optimal event in terms of signal noise. It's closer to the ones you expect. And yet you can't really set a useful limit on the tidal deformability. So the question is, how many events do we need to get before the limit starts being constrained?
So that's a great question, and keep in mind that we're still a factor of 3 sensitivity away from design, right? So if we get this in 2020, it's going to be SNR 100, all right? So that's going to help a lot. I also think that probably, realistically, we maybe do a little better with this data. Some people are working on basically turning a couple more knobs to make this estimate better. But otherwise, I mean, folks have done these estimates, and with many more events in advanced LIGO, you can start to constrain the tidal deformability. I think this scenario is even more optimistic than what people published papers on because the event rate is higher, and the probability of us getting an SNR 100 before, by 2020 is decent.
Also doesn't, I mean, a lot of the constraints you're able to place on the deformability come from the high frequency sensitivity, right?
Yeah, it's because it's late in the in spiral, yeah.
And so, I mean, I don't know if you just scale the current sensitivity down to design. I mean, isn't that my understanding from what Zuza said that basically we're going to do a lot better as we turn up the laser. We're going to do better at high frequencies. I guess I'm asking is it partially that we haven't got the sensitivity at high frequencies that will also affect, I mean, it isn't just a matter of SNR, it's where your sensitivity is, right, too?
Yeah, though I don't. Yeah, you're absolutely right. I wouldn't be more optimistic than the statement I just said. Though.
Okay.
Because I think, you know, the laser power, as Susa would say, you know, it's quadratic for laser power, right? So like you've got to get a factor of 3, you got to 10 times more laser power, and that's just not going to happen.
But
Period.
we
But we have the
200
squeeze.
watt
We've got the squeeze.
laser going in there, so that's the top, and then we can get the factor of 2 and squeezing. Yeah, no, I mean, I am not sure we are gonna see any of those post-merger waveforms, if you ask me, with advanced LIGO. I'm not saying we will not look, I'm sure we will, and I hope I am not right, but, you know, it's not easy.
Could you explain your first question?
Oh, sorry.
Could you explain your first question? Does that just mean that the transients associated with this event would not have been seen without the trigger? Is that what you're saying?
Yeah, I
Or
mean.
is there another meaning?
So I mean this to mean like in a completely broad sense, but I mean the fact of the matter is that this GRB was 10 times closer than what we had ever gotten a distance for. My understanding, I'm not an expert on this, but my understanding is there are some selection effects probably in the current instruments for seeing these sorts of off-axis things. But if we can have access to this somehow and follow them up, there may be others that we can ultimately get to. I guess that's my main point. Is, you know, this one would have. I don't know if anyone wants to comment if they think this is wrong, but from my understanding, that the odds of this thing being followed up without the gravitational wave trigger is basically 0. It's uninteresting in some sense, and it's poorly localized, and there's just so many reasons why probably no one would look. So we just need to be rethinking that now that we know these things. That was my only.
So back to the title.
Can we,
How much did the glitch?
Sorry.
How much did the glitch affect your ability to measure that?
Very little, surprisingly.
Really?
Yeah, and the reason is, sorry. That one graph makes it look a lot worse than it is. It's actually very narrow in time, so you can kind of just cut out those samples and integrate right over it, is what it boils down to. So as long as you know how to remove them, which people do.
Well,